Okay, G, I think we should have to start. What is your opinion? May I start or not?
सर स्टार्ट कर लें
Okay, that's good. So, uh, this is basically the outline of the lecture that you are seeing, and it is containing of the evolution of genetic algorithm, and then we will see genetic algorithms, particularly not only their evolution. Evolution means starting from the beginning to the concept of evolution. And then we will see some examples of genetic algorithm accordingly. And finally, there are two small topics. One is contingency, and other is online search that you have to study by yourself. So let's start properly. But before starting, I want to inform you that this topic is from your another book, which is mentioned in your outline document of the course, which I have given to you in the beginning. And in that document, this book is mentioned as reference book number 1. And there is another book that is reference book number 2, but this is reference book 1. So this topic is from that book. So if anybody want to read it in detail, that then he or she can go towards that book, or you can also read it through different sources, because one source is not enough. But this is only uh, a guidance actually. If you want to go directly somewhere, then this is the book actually. So one thing which is very much common is that genetic algorithm, we normally have an introduction of genetic algorithm that it is some kind of single algorithm, but actually it is the collection of 3 to 4 different small sub algorithms actually. For example, you have to create some kind of population, and then you have to calculate some fitness computation function, and then you have to calculate then you have to do the selection actually, and finally you have to recombine some things actually. So these are only 3 or 4 um, uh, concepts and sub-algorithms that normally gathered in one form, and that is called genetic algorithm. So genetic algorithm, we can use this genetic algorithm to solve different problems in different fields. But the only thing that we have to take care of is that how we can fit this genetic algorithm to our problem. So this is something you will get when you will practice this genetic algorithm in your student life, and then with this practice you will uh, get this idea how to fit this problem in different uh, how to fit this algorithm in different problems actually. So this is some kind of an introductory statements for the genetic algorithm, and now let's move on to its evolution. As I said, evolution is some kind of the knowledge or the history from the beginning to the concept, to the developed concept of genetic algorithms. So this area particularly, uh, from the beginning to this developed idea of genetic algorithm, this area is basically the area of evolutionary strategies. At that time, there was no name popular for the genetic algorithm. Genetic algorithm was not known actually. People were calling all these strategies as evolutionary strategies. And in those evolutionary strategies, there is a concept of, there was a concept of population. And initially, and population means you can consider, okay, some kind of a pool in which you have to place the data. So that is population. So the size of the population was restricted only to 2 members at that time, in the beginning, not now actually. And those 2 members were the parent and the child, as you are seeing in this uh, first statement on this slide. So, so in the beginning, you have to keep this in your mind. In the beginning, there was no name for the genetic algorithm, and the people know most of the strategies which are a little bit intelligent, you can say. Then normally people categorize uh, those schemes or those algorithms in evolutionary strategies, and especially things related to local and optimized searches, they normally keep in this category of evolutionary strategies. And there was a concept of population, and population only contains 2 members. One is the parent, other is the child. And at that time, the child was modified randomly, or you can say, if we have parent and child in a population or in a selection, then the child was randomly modified through only mutation operation. So this is another thing, that at that time there was only one operation available for modification, and that is called mutation. And mutation is what, and and I am sure that you have seen the movie X-Men and many others movies of mutants. And in mutants, mostly we are the Homo sapiens, we are the humans, but maybe there is one kind of difference from the Homo sapiens, in that particular different characters available in those movies, and that difference is the modification actually. So, in these studies, in the beginning, uh, in those studies, the child member was selected randomly for the modification, and that modification was called mutation at that time. And now we know that in our population we have the parent and the child, and from the parent and the child, the member which was more fit, was selected to propagate towards the next generation. Propagate means you are allowing that more fit members to perform some recombination operation. Or, by the way, mutation is also the recombination operation. So you can simply, I will explain these propagation, but this is something that now you are allowed to go or to move on to the next generation. So anyhow, as for example, this is the picture displayed here, and in this picture, there are 4 generations displayed. One is generation, and this is T0, generation T1, generation T2, generation T3. And in each generation, we have the parent P and the child C, and some values, fitness values, are mentioned along with each member. So here we are seeing the parent has the very fitness value F is equal to 5.6, and the child has the fitness value F is equal to 9.1. So this child has the more fitness value. So then this child will be allowed to move on to the next generation by performing some recombination operation. Or so now the other member with less fitness value would be dead actually, only, and that member will have the life only for this generation. So in generation T1, we have the parent with fitness value 9.1, and the child with the fitness value maybe 8.7 or something. And now this parent again has the higher fitness, so this will be allowed to move on to the next generation, uh, uh, generation T2. And similarly, this child has more fitness, so it is allowed to move on to the next generation. And similarly, this child has the more fitness value, and it is allowed to move on to the next generation if some generation is available. So this is basically the simple concept of generation. I'm not saying now the genetic algorithm, because this was the time when there was no name of genetic algorithm was available at that time. And these studies were known as evolutionary strategies. But this is something, the evolution of the genetic algorithm, because this is something has the same concept as the genetic algorithm is containing. So now let's move on. And this is another example that at that time of evolutionary strategies, basically why this, in this slide, there is a string mentioned here, and then there is some finite automata and its transition table displayed here on this slide. So why we are going to understand some kind of finite automata or theory of automata related thing here. Actually, at that time of evolutionary strategies, we know that there was no name for the genetic algorithm, but for example, this concept was being in use at that time. So, and in this concept, there is a concept of string, because these members that we have in this generation, these members can be represented by strings, or could be represented by strings at that time. So there is a concept of strings in these evolutionary strategies. So that's why this slide is giving you this information about the strings. And this is one way to represent strings. There may be different representations for the string, but this is one way. And in this string, are you listening me? Hey, my students, are you listening me?
Yes, sir.
Okay, good.
Yes, yes, sir, we are listening.
Okay, that's fine. So this, so we have this string, and the first digit in the string is 5, which means the number of state. And this string is for this finite automata. Maybe you don't have studied theory of automata in your discipline, because this is the software engineering, not the computer science or the IT. But most of the...
Sir, in formal method, we have idea.
Okay, then it's fine. Then I hope that you will understand this string also. So in this string, the first digit, the first symbol is simply depicting the number of states in your finite automata. Because this is a string for the finite automata, this is the finite state machine, or finite automata, you can say. And how many states in it? 1, 2, 3, 4, 5. So this 5 is for this purpose. And then the second digit here in this string is 3, which means you can perform 3 transitions from every state. So this is a state, and this one arrow is one transition. So this 3 means you can perform 3 transitions from this any one state of this machine. And what are those transitions? You can, for example, you can take an A and you can move on to the state 1. You can take B and you can move on to the state 3. And simply from state 4, we can take plus, and this is the end or the termination condition of this finite automata, that here the machine will end. So there are 3 transitions, A, B, and plus, available only for this particular example. So that's why it is 3 mentioned here. So that which means that the number of transitions available. And now these are simply the triples available here in different forms. The first triple is for state S0. The second triple is for state S1, and similarly S2, S3, and S4. So this triple is saying that from S0, I can take A and I can go towards state 1. This 1 is for state 1. And the first, in each triple, the first digit is for A, the second is for B, and the third is for plus. These are the transitions that we have, these three transitions. So what this triple is saying, this triple is saying that we can move on from S0 to state 1 by taking input symbol A, so this one. And this state is saying that we can move on to state 2 by taking A again. So by taking A again, we can move on to 2. And similarly, the last one. Rest of the things are same. This is for B actually, and this is again for B. And this is, we can move on from state S4 to state 1 by taking A. From state 4 to 1 by taking symbol A. And similarly, X means from S4 by taking B, there is an error. There is no any transition available, you can say. So from S4, X means there is no any transition available. Or you can, here it is mentioned as error, but it actually means there is no transition. Or if you apply some input here, then you will get error actually, because there is no transition available there. Okay, finally, from S4, we can take plus, and then we can reach at termination condition, or simply the T is mentioned in the transition. From state 4, we can take A and we can reach at 1. From state 4, we can take B and we can reach nothing to nothing. So nothing means an error, there is no transition. And from state 4, we can take plus, and then we will reach at the termination condition. This is basically termination condition. We can again draw a circle over this and we can make a state, but it is mentioned that in this representation, we are considering only 5 states, not more than that. So now I hope that you have the understanding of this string, and if this string will be given to you, then you can make this finite state machine, and also you can make this transition table through this string. Is it clear or not?
Yes, sir.
Sir, should be complete if state 1 take A, then it should also take B as output, or
we are not studying theory of automata, okay? So this is, for example, there is no need to complete all the transitions at every state, because we are just getting the concept. So this is non-finite automata, you can say. This is not deterministic otherwise. The things that you are mentioning are something related to deterministic finite automata. But this is not the course on which we are focusing. We are just getting the concept of this string. Okay, that's fine.
yes, sir.
Any other thing?
Fine, sir.
Okay.
Clear, sir.
Okay, move on to the next point. So here comes the proper concept of genetic algorithm. So before that, there was no name as genetic algorithm. Rather, the strategies or the techniques people were using at that time, the same techniques with this new concept of genetic algorithm. Those techniques at that time were known as evolutionary strategies. But now on this slide, we will see that there was a person, that name was John Helland, And in 1960, he come up with an idea of this genetic algorithm. John Holland, according to the text, it seems to be a biologist, and is this theory of genetic algorithm has more resemblance towards the biological concept. So that's why it is mentioned with greater biological plausibility, which means that his theory of genetic algorithm were more reasonable to biology and not to any other field like computer science or anything else. So because he used most of his terms and explanations from the field of biology. So initially, this theory or this algorithm is for the biology and not for the other fields. But later on, the persons or the scholars from the other field, they have studied this theory and they have taken the idea and they applied the same concept of this genetic algorithm in other fields, like we have now this theory in computer science. So in evolution strategies that we studied earlier, in that strategies we have only one operation, that is called mutation. But in this theory of genetic algorithm, or you can say in the algorithm of John Holland, in the algo of John Holland, he added further operations in this theory of evolutionary strategies, and it gives its name a genetic algorithm. So he added and extended the existing theory with additional operators. And what are those operators? For example, one which we already have seen, not understood, but we have seen at least. We at least have got the name of that operation, and that is mutation. And the other one is the next edition of John Holland contains some other operators, and these operators are crossover and the inversion. We will see these operators, three operators, mutation, crossover, and inversion in detail in the next slide. We will see these things. But up to now, for example, we only have to keep these three operators in our mind, that these are existing. And then later on, we will see these operators in detail with the diagrams and the figures. John Holland used another terms, potential solutions and the chromosomes. And he come up with the strings of bits instead of real values. For example, this is the diagram of John Holland's idea. And in this population, you are seeing that there are different members, and there is not now only two members. In previous studies of evolutionary period, there was only two members, parent and child. But now in the population, you are seeing more than two members. So 1, 2, and so on up to nth. So, and these strings are the representations of the various members. This is one member, this is second, third, fourth, and so on. So these strings, these bit strings are called potential solutions, or also called chromosomes by John Holland. So why potential solutions? Because these are the candidates for giving us a solution, or these are the candidates which have the tendency to give us or to provide us some sort of a solution. So that's why John Holland call it potential solutions. And John Holland used other particular name with respect to biology for these members as the chromosomes. So for John Holland, these are the chromosomes, and these are also the potential solutions. We can also call it members. We can also call it parents. So anyhow, there are different names. So mm, as far as the chromosome is concerned, we are not the biologists, so that's why I have just written some statements about the chromosomes, what chromosome is. So in all living organisms, for all uh, for all of the living things that we have in our world, it consists of some kind of cells, and in cells we have a set of chromosomes, and in chromosomes we have strings of DNA. So particularly we have to focus on chromosomes. So we have cells in our body, and then we have set of chromosomes in those cells, and in each chromosome there are the genes. Or you can say chromosomes is made up of genes. And what are genes? Genes are simply encoding the physical and the mental or behavioral traits of us. For example, what would be the shape of my nose, ear, eyebrows, and the whole face and the whole body? What would be the shape I will get after 1 year or 2 years? This is coded in our genes. And what are the different things I will do or I will act according to my attitude and according to my behavior. These are also already encoded in our genes by the Allah Almighty. So now you can understand the programming, a little bit programming of Allah Almighty. So when normally uh, a child comes into this universe, then all the things that will happen um, with that baby um, with respect to behavior and with respect to his physical shape is already coded by Allah Almighty in our genes. So you can read it here, and this is something very interesting topic. Seems very interesting topic. So, and now I can come back to this diagram. So this is the population, and we have the chromosomes are the potential solutions, are the members, are the parents. I am just repeating all the names for you so that in future you will feel easiness to understand different terms. So this is the population. From the population, the next step that John Holland has in its genetic algorithm is that next step is called the selection. In selection, John Holland normally take or select some members or parents from this population, and then after selection, there is another step that is called recombination. And in recombination, we have three operators: mutation, crossover, and inversion. So in this recombination operation, the parents are the members that John Holland has already selected. Then he performed this combination or recombination uh, operation over it. This is just and it contains mutation, inversion, or crossover. So you can consider this is the crossing of the two parents, and after crossing of the two parents you will get new members, and then again you can keep or you can place those new members again into this population. So this is the normal idea of the uh, John Holland's genetic algorithm. But we will see this idea in detail in the next slide. But before that detailed idea, here this slide is simply giving you the concept of crossover operator. Simply concept of crossover operator. Because we are using this crossover operator already in different things. This can be the topic, this expression, this topic of combination of expressions, recombination of expressions, mixing of expression. This topic basically, this is the topic of data structure, and also you can say in theory of automata, but mostly are mainly as the part of data structures. So here in this slide, what we are saying that we have one expression x square plus y square, and then we have another expression x plus y square. And this is the tree for this expression, and we are calling this as A, and there is another tree for this expression x plus y cube, and we are calling this tree B. If we mix these expressions with each other, then what we will get, so we are not allowing or following some kind of rule here. No, we are not. We are simply just taking the concept of crossing between two trees or expressions. So according to the crossover operator that is available in genetic algorithm. So this illustration is according to the genetic algorithm, just to get an idea what crossover operator is. But detailed explanation, detail of crossover operator we will see in the next slide. So this is just only the understanding. So if I will keep this tree, or I will place this tree over this tree B, then what would be the shape I will get? That shape would be like this. That shape would be like this. And this new tree that we have on this slide, we can call it B plus. So, and this tree B plus is containing the properties of A and also the properties of B. How you can infer it? We can infer it. For example, maybe I have this annotation tool, and at this moment, I think this annotation tool would elaborate the things clearly. So this is your A tree, and this A tree is, for example, this is your A, and we know that. This is exactly my A tree in B plus. And similarly, I can find, sorry, something happened with my slides on my computer. So just give me a minute so that I can set up the whole things again.